Good afternoon and welcome to the CERIAS Security Seminar from Purdue University. Our speaker today is Andre Koenig from University of Illinois at Champaign, but he's a visiting scholar there from the Technical University in Darmstadt. His topic today is security and infrastructureless decentralized systems. Andre.
Okay, thanks a lot for the introduction. Thanks for inviting me. So I thought I would try some different kind of motivations. So let's see what security and infrastructureless decentralized systems has to do with this jungle. So starting a talk on communication networks with something like, by now communication systems have found their way into many areas of our everyday life, would be quite legitimate, I think. But for two reasons it won't work for this talk. And the first reason is exactly this way. So when we're talking about the way, we're talking about something like infrastructure. So for communication networks, this would be wires, routers, access points, wireless access points, but also cellular base stations. So communication networks today, when you think of wireless communication, are well able to live without these infrastructures. And that's exactly when we are here. So let's try to go back to the infrastructure part and talk about security. So for our well-known infrastructures, communication infrastructures, we are quite secure within these. So we have defined authorities, we have defined means to control access to these infrastructures, and we have defined means to detect and deal with misbehavior. So when we leave our well-known communication infrastructures for which we know security mechanisms that will work, we're confronted with new challenges. So maybe new types of misbehavior, and maybe for these types of misbehavior, the security mechanisms that we defined will not work anymore. So the second reason why this introduction would not work for this talk is the everyday life. So I'm not going to talk, and I will want to show this very short in one picture. I'm not going to talk about communication networks for our everyday life. So to wrap this up, I'm going to talk about peer-to-peer systems on mobile ad hoc networks. So in fact, the decentralization and lack of infrastructure on the whole network stack, and this combination is mostly mentioned in the context of first responder scenarios. So scenarios where communication infrastructure is not or not anymore available. Within these scenarios, we have specific properties. So in general, they are highly dynamic, so we have a constantly changing topology. We have no communication infrastructure as said, so we need the wireless transmission to connect the devices, and the functionality of the resulting network will be based on cooperation. This means if we want to have a communication between two nodes that are not in direct transmission range, then we require nodes in between to relay the communication appropriately. So from the perspective of security, this is challenging because it means that we won't have well-defined network borders. So nothing that we know from infrastructure-based systems that can be protected by means such as gateways or firewalls, for example. And we won't have central trusted instances, so something upon which mechanisms like public key infrastructures or authentication, accounting, access control, Kerberos is based on. So to conclude the motivation, we can say that with the decentralized infrastructureless systems, we can offer communication beyond today's communication networks, beyond wired, fixed, infrastructure-based communication networks, but we are also beyond the protection of today's security mechanisms. And these are exactly the challenges I will talk about in the following. So I will talk about security mechanisms, novel security mechanisms for peer-to-peer systems and for mobile ad hoc networks. For both areas, I will introduce shortly the basics just to get us all in line with the foundations we need to understand it. I will show evaluation results, and I will show models, testbed experiments, and I will talk about the challenges we have when we want to evaluate new protocols, new mechanisms for decentralized and infrastructural systems. So if you have any questions regarding the understanding what I'm saying, feel free to ask at any time. So let's start with security in peer-to-peer systems. Just for the basics, the challenges in peer-to-peer systems, two main challenges we have is how do we perform service lookup and how do we offer security? That's what I'm going to talk here. So just to compare with client-server systems, there we have a very clear role assignment. We have servers that offer services and we have clients that consume services. And services such as service lookup, so if I'm looking for some content in a client-server system, I will have servers that are in duty for this. So when I'm talking about World Wide Web, I will have something like Google. When I'm talking about service-oriented architectures, I will have some service repositories maintaining directories of the services available. In client-server systems, also the security mechanisms are offered by servers, by central trusted instances. So, for example, public key infrastructures for key management, for mapping identities to a communication network, to cryptographic keys. And for example, something like Kerberos for authentication, access control, and accounting. So in peer-to-peer systems, we do not have these role assignment. We have services offered and consumed equally by the peers. So no servers, no central trusted instances. The main question is how can we perform service lookup? How can we offer security mechanisms? Just for the service lookup, because we will need this in the following one slide. There are 3 ways to do this. First one is unstructured peer-to-peer systems, and here a peer just joins, and if I want to access services that are offered by the peer, I will just broadcast a request in the whole peer-to-peer system. In hybrid peer-to-peer systems, there are some super peers defined to which I announce services, and when I'm looking for a service, I will address a super peer and ask, hey, which peer offers me this service? So problem is, how can I assure that my request for a service would reach the appropriate peer, and how can I make sure that I will really discover all services that are within the network, and both is a bit challenging for unstructured and hybrid peer-to-peer systems. So what I will use in the following is a structured peer-to-peer system, in fact Pastry. These are based on distributed hash tables, so these work quite like phone books. If you imagine peer-to-peer system, structured peer-to-peer system consisting of, to make it easy, 26 peers with the IDs A to Z. Then peer A will be responsible for services that start with A. So if I'm looking for a service that starts with A, I will exactly know which peer to ask for, and he will have the information on which peer this service will be offered. So just for the performance, Pastry offers a prefix-based routing. In general, structured peer-to-peer systems offer routings that are based on tree structures or ring structures, and within these we have a logarithmic lookup time with respect to the peers, total number of peers that are in the system. So what I'm considering in peer-to-peer systems are cooperative decisions as a replacement for missing central trusted instances. So if we do not have central trusted instances available and want to decide on security-related requests, we have to make sure that we need a way to decide on this, and we have to make sure that not one single peer is able to decide on a security-related decision. So not one single peer should be able to grant access to restricted resources. So, and for this we need, on a technical level, some means to distribute cryptographic operations. So in fact, not a single peer should be able to sign some certificate that grants access to restricted resources. What we use for this is threshold cryptography. This is based on Charming secret sharing. It's in fact a way to distribute the keys. So you define a polynomial such that the value of the polynomial at point 0 equals the key you want to distribute, and what you give to the peers are values of the polynomial at specific index values, and depending on the degree of the polynomial, a certain number of peers have to interact to perform cryptographic operations. So for peer-to-peer systems, if we talk about signing certificates, what will be done is to have partially signed certificates signed with the key shares that can be interpolated to a fully signed certificate if you have a specific number of partially signed certificates available. So we're not the first ones that apply threshold cryptography in peer-to-peer systems. There is a lot of related work, too, by groups of Narasima and Saxena. They considered applying threshold cryptography for admission control. This is for who should be allowed to join the peer-to-peer systems or a mobile ad hoc network. And what they considered, they compared different approaches of threshold cryptography with respect to the computation time that is needed to produce one partial signature and the join time, which means how long does it take from the point I send my request until I get enough replies to be able to interpolate such a certificate. So they consider technical metrics. What no one has done so far is to think about the decision policies, so security policies that are required to define how our security-related requests should be handled. So if we think about peer-to-peer systems in these application scenarios, so in first responder scenarios that are established spontaneously, we cannot assume that security policies for every security-related request possible would be available. So in fact, what we propose is just to use user-based decisions. That is, we authorize users by giving them key shares, and if a request should be handled that is not predefined by security policies, then the users will be involved directly. The question at this point is, how many users do you want to involve? So certainly you do not want to wait some 2 hours, 3 hours for a decision, but you do not want to involve too many users, because if you consider something like a pop-up coming up when a security-related request should be handled, then this will annoy the user. And when you think about, for example, installing something like a personal firewall, which pops up every 2 seconds, what you do is just click yes, go on, leave me alone. And we surely do not want to happen this in our scenario. So we wanted to design some mathematical tools for governing this decision process. So we wanted to design tools for limiting the number of users that we involve in one decision process, still having a probability that is high enough that decision process will be completed within one round of asking and replying. So when we want to design these tools, what we need to know is how the peers interact in the decision process. And we said, okay, this can be either a non-mediated multicast or a mediated multicast. This depends on whether the peer that distributes the requests has knowledge about the distribution of key shares within the network or it doesn't. So if I do not have knowledge about the distribution of key shares in the network, what I can do is, for example, just to send a request to some arbitrary peers. So in this case, I might hit peers that are not authorized to take part in the decision, and I may hit peers that are authorized to take part in a decision. So regarding free pastry, this can be done by some probabilistic forwarding, by some gossiping approach, or by just selecting random peer IDs and addressing them. So mediated multicast means that I have some peer within the network that has knowledge about the distribution of key shares and that has knowledge on the status of users. So something like the Skype status saying, okay, this user is currently not under heavy load, so he or she can take part in the decision process. So regarding the implementation, this can be done by introducing some coordinating peers, so one dedicated peer. This can be taken by whatever peer. So if the peer leaves the network, it can be switched. Or by having some multicast approach, so we implemented based on Scribe. So we have a multicast group that peers that are equipped with key shares, that are authorized to take part in decisions, and are ready to do so, can join a multicast group, and you can just address a multicast group saying, hey, I need a decision on a security-related issue. So coming to the mathematical tool set, the goal was to control the number of users requested, to minimize the number of users requested. And for this, we developed a success model. This is if I have factors like the total number of peers in the overlay, like the number of peers that are authorized to take part in decisions, like the number of peers to which I send a request, the threshold that is given by threshold cryptography. This is how many replies, how many partially signed certificates do I need to be able to interpolate a fully signed certificate. And considering the probability with which one peer answers a request in an appropriate amount of time. Then we want to have the success probability. This means the probability for receiving enough partially signed certificates to be able to do the interpolation and to have the decision made. Okay. So for the non-mediated multicast, this model is based on a hypergeometric random variable. And this hypergeometric variable describes, in fact, the intersection of the sets of peers that are authorized to take part in decisions, that have key shares and that are ready, and the set of peers that we address. And so this is the probability for receiving one specific number of replies. What we are interested in is not receiving one specific number of replies, but receiving enough replies to be able to do the interpolation. So receiving at least enough replies to satisfy the threshold. So we start to sum up this hypergeometric distribution at a certain point, and with this we get a success probability. This is quite, the result is quite straightforward. So if we have everything fixed and we vary the threshold, we see that with a lower threshold we will have a higher probability for success. If we have everything else fixed and we vary the number of requests that we send, then with an increasing number of requests we will have an increasing success probability. So for the mediated multicast, the number of receiving one specific, the probability for receiving one specific number of replies can be described by a binomial random variable. We also sum up this at a certain point. This is the threshold, and we get to this description of the success probability. I don't want to go deeper into the math here. If you have any questions, just feel free. We can have a common closed form for both models, for both interaction schemes. If we approximate the hypergeometric random variable by a binomial random variable, then we will be able to apply Chernov's bound to have a lower bound for the failure probability, and with this an upper bound for the failure probability, and with this a lower bound for the success probability. So what we wanted to do is to validate this model in real world, so to see whether the model describes reality or not. And we had two test beds available for this. One is Planet Lab, so you all might have heard of Planet Lab. Currently consists of 1,000 nodes distributed at 500 locations worldwide. Issues when you want to evaluate peer-to-peer mechanisms is first the size of Planet Lab, because if you think about 1,000 nodes in contrast to peer-to-peer systems like, for example, Skype, consisting of tens of millions of nodes, this is clearly one issue, is the size. And another issue is the correctness of the experimental results, of the testbed results, because behavior of Planet Lab is anything but predictable. This is good if you want to do an evaluation in a real system. This is bad if you want to have reproducibility for your results. Second testbed we had available is GLab. This is a German national project. In fact, we're about to set up an experimental platform for future internet research, and currently it runs on Planet Lab software, so it was quite easy to rerun the experiments we performed on Planet Lab on the GLab testbed platform. So also here we have comparable issues. The size is actually less than Planet Lab. We have currently about 175 nodes, and the experimental results that we have a quite good control over this testbed. We can reserve it and we can have it exclusively for one portion of time, but this makes it quite unreal with respect to the correctness of the results. So to give you an idea what this means, we performed an experiment. This is for the non-mediated multicast scheme to validate the model. We had 100 peers, 25 key shares distributed within the system. We set the probability for one peer to answer in an appropriate amount of time to 50%, and we sent out 58 requests. And what we observe is that this figure shows the success probability subject to the threshold. This is quite straightforward. If you have everything else fixed and increase the threshold, then the probability for receiving enough replies will decrease. And what we observed is a quite good match for the model predictions shown in red, and the results from Planet Lab. What we did not have was an exact match of the model predictions or the Planet Lab results to the results of our national test bed. We're currently just about to find out what this means, and we're currently about to adapt the model to add some more degrees of freedom to match both cases. But I think it's just an interesting point that if you rerun experiments on 2 different test beds and you get different results, then we will clearly have to be very meticulous when we want to run test bed experiments to verify mathematical models. So, second part of my talk will be on security in mobile ad hoc networks. So just for the basics, since mobile ad hoc networks are completely infrastructureless, the nodes have to act both as communication endpoints and as routers. So if 2 nodes want to communicate and are not in direct transmission range, then the nodes in between are required to relay the transmission. This means the routing in a mobile ad hoc network has to deal with a constantly changing topology, so it has to deal with a very high dynamic. And there are, on an abstract level, there are 2 approaches to deal with this. One is a proactive routing, which broadcasts link state information periodically, and so a route will be available before it is needed. And the other one is the reactive approach, in which a route is looked up at the point it is requested. And this is in fact what I will use in the following. So I will use ADV, and it works just like if I have a source that wants to communicate with a destination and no route is available, then a route request will be sent as broadcast, and as soon as the route request reaches the destination, a route reply will be generated, and this route reply will be sent back, and with this a route is established. So to minimize the broadcast overhead for broadcasting the route request, ADV will use an expanding ring search. This means we will start looking for the destination in an area close to the source, and if it is not found, we will increase this area in certain steps. So we will use this later on. So regarding security of mobile ad hoc networks, in fact, due to the wireless multi-hop communication, and if you consider devices from many administrative domains, then mobile ad hoc networks are vulnerable inherently. So in fact, each layer is affected by new types of attacks. We have simple jamming on physical layer and medium access layer. We have more sophisticated means, for example, a transport layer. If you just delay TCP acknowledgements, then you will start the TCP fallback mechanism, and you will decrease throughput in the network. And these are attacks that become available due to the wireless multi-hop nature. So what we consider is attacks on routing layer. These are in general based on injecting false routing information, and one attack that I will use in the following is the black hole attack. Just like a black hole in terms of astronomy, black hole in a mobile ad hoc network tries to attract traffic and does not forward it, but just drops it. And in this case, it's quite straightforward because the black hole is closer to the destination, so the route appears to be better, shorter, more reliable, and the source will choose this route. Anyway, the black hole can lie about these routing metrics and pretend to have good routes to any possible destination, and with this attract traffic, and then if it comes to the data exchange, it will not forward the data, but just drop it. So question is, how can we deal with misbehavior in mobile ad hoc networks? How can we exclude misbehaving nodes, since mobile ad hoc networks are vulnerable inherently? In fact, there are 2 approaches. One is intrusion prevention. Other one is intrusion response, intrusion detection combined with intrusion response. So intrusion prevention is usually based on secure routing protocols, and these use means of cryptography to secure route discovering and to secure routing tables to prevent false routing information from being injected or correct routing information from being altered. Question is, if we use this on routing layer, on network layer, how can we prevent attacks on other layers? And in general, this is not possible by secure routing protocols. Another example are secure ADV and Ariadne as a secure version of DSR. And these protocols have been designed very, very cautiously. In fact, still attack vectors have been identified recently that are able to circumvent the cryptographic mechanisms deployed in these protocols. So what I will talk about is the second alternative, intrusion response. There are several approaches available. The first one was, in fact, watchdog and path rater, proposed by Marty. And this is just, if we consider the black hole attack, the intrusion response works just like overhearing whether a node relays the communication correctly or not. So if I send to my direct neighbor a packet for forwarding and assume symmetric wireless link, which is in fact good assumption, because if we consider 802.11 with an RTS-CTS sequence, we need a symmetric wireless link, then I will be able to overhear whether my neighbor relays the communication or not. So, and if it doesn't, I can just mark it and say, okay, bad one, don't use it for routing. Subsequent approaches like confident co-notion, they try to overcome some drawbacks of watchdog and path rater, but they are still based on this overhearing approach for intrusion detection. What they all do is to use an address-based approach for intrusion response. So to exclude a misbehaving node from the network, they just say, okay, this is a bad address, do not send anything to this address or do not receive anything from this address. The question is, if we are in a network where we need the cooperation as a basis for functionality, and if we have devices from many administrative domains, so in general, a user can just do whatever he or she wants with the device, then changing addresses is possible very easily. It may be on a medium access or network layer. And with this, we can just bring down the effect of address-based intrusion response mechanisms. So we said, okay, let's try it another way around. Let's try some location-based intrusion response. And the idea is quite simple. We set up quarantined areas. If we detect misbehavior in a network, we define a quarantined area where the misbehavior happens. And this is, in fact, a three-step process. We have to establish these quarantined areas and to interrupt routes that are affected, so that cross these quarantined areas. Second step, we have to establish routes that do not cross these quarantined areas. And for ADV, we do this just by restricting the broadcast of a route request message. So every node located within a quarantined area is not allowed to relay route request messages. And with this, the route established will just go around the quarantined areas. And in a third step, since we assume that tracking of the nodes is not possible while they're quarantined, so if there is no communication, then you won't be able to determine locations. We have to revoke these quarantined areas after a certain amount of time, because otherwise what will happen is, since we are in a mobile environment, the misbehaving node will move, will have a new affected area, will become active again, will become detected again, a new quarantined area will be set up, and with this you start to partition your network, and this is what we want to avoid. So we revoke these quarantined areas after a certain amount of time. So also for mobile ad hoc networks, I want to talk about evaluation issues. Mobile ad hoc networks are not as widespread in real world right now. There are some, but they are designed for real data transmission, and the people running them wouldn't be that happy if we want to implement attacks and countermeasures within these networks. There are a few testbeds available, but these are usually designed specifically for the needs, so for the research that should be done within these testbeds. So the results would be comparable, very hardly even worse than for the peer-to-peer case. So we decided to go for simulation studies and for analytical models, just to have two points of view on the problem. So both simulation studies and analytical models have to make abstractions, simulation studies, because otherwise you will have runtimes that are not feasible anymore, and analytical models just because you won't be able to handle everything from data transmission up to routing protocols. So since simulation studies can only cover some small portion of the parameter space, we said, okay, we will have an analytical model to cover the rest. So these are simulation results from the studies we did for the location-based intrusion response. We had a scenario consisting of 1,000 nodes, 7 to 8 neighbors per node. This means we just have a connected network, so the probability for having a route between arbitrary nodes is some 99.9%. We have a mobility with pedestrian speed, and we have 1 hour simulated time per parameter set. So what is shown here is the results for a defenseless network when you increase the number of black holes considering the loss that is caused by the black holes. And you can see that just one black hole in our scenario consisting of 1,000 nodes is able to attract more than more than 60% of the traffic, and if you increase the number to some 5 or 10 black holes, which is just 1% of the nodes in the network, then you will have drop ratios, loss caused by the black holes of more than 90%. And if you consider that there will be some inherent loss due to collisions, due to route breaks, then this network will be down. So for the address-based intrusion response, we considered also the loss that is caused by black holes, but subject to the frequency with which misbehaving nodes change their addresses. So in fact, intrusion detection system will detect a misbehaving node, and after a certain time, this misbehaving node will change the address. And if you exclude a misbehaving node based on its address, then you can circumvent the countermeasures. So what we can see is that for low frequencies, so for static addresses, the address-based intrusion response works quite well. If you start changing the addresses, then the loss will increase, and the effects of the address-based intrusion response will decrease. This is quite straightforward. And in fact, this is a quite simple approach to circumvent address-based strategies. So you can have some more sophisticated ones by saying, okay, if I do not receive as a misbehaving node, if I do not receive data for some amount of time, I will change my address. So you can even improve this effect from the perspective of the misbehaving node. So for the location-based approach, we evaluated the loss that is caused by black holes subject to the quarantine time. This means the time during which one quarantined area is active. And clearly, if we choose this too short, we will have a bad effect on loss, so we will have quite high loss rates. If we optimize this, and in this case, the optimum is that, so for the scenario given here, the optimum is about 300 seconds quarantine time, then we will have loss ratios that clearly outperform the results from the address-based response. If we are confronted with misbehaving nodes changing addresses, yes, please. Pardon? Mobility model is a random waypoint model. No pause time. It's between 1 and 2 meters per second. So it's a pedestrian scenario. And in fact, we split up, because if you use a random waypoint model, which is kind of a worst case model regarding mobility, if you have more predictable scenarios, then we'll be able to optimize countermeasures, something like wireless networks for cars, for example, vehicular ad hoc networks. Anyway, to reduce unwanted effects of this random waypoint model, because when you use random waypoint model, the nodes tend to go to the center, and we split up the simulation time. So we used simulation time, and we had several runs. So this 1 hour is split up into several runs consisting of some 5 or 10 minutes, just to limit the negative effects of these random waypoint model. Okay. So other questions on this? So the second point we have to consider is the loss caused by intrusion response. And we charge packet loss to the intrusion response from the time misbehavior is detected until it takes to inform the source and to stop sending data. So it takes some time. When the intrusion is detected, there is an error message sent back, and during the time this error message travels to the source will still be sending data, and this data will be dropped, and we charge this to the intrusion response and not to the misbehavior anymore. So for the address-based intrusion response, this loss is quite low because we just exclude one singular point from the network, just one node. If we consider the location-based approach, this is clearly a drawback of the location-based approach because we do not exclude one single point from the network, but exclude a certain area from the network. So we also exclude nodes that are located in proximity to a misbehaving node, but are well-behaving, so could be used for routing. So this is clearly a drawback which we addressed in further work, and I will come back to this later. So this is the overall loss. Just to give the comparison, you can see that the curve of a defenseless network is raised by some 10% compared to the black hole loss. This is due to inherent loss, and here you will see that we are far above 90% for 10 misbehaving nodes and nothing will happen anymore on this network. So also for the address-based response, the results we saw from the last slide are raised due to inherent network loss. But what we can see is that although we have higher loss for the address-based, for the location-based approach than for the address-based approach, due to the intrusion response mechanism itself, we're able to have a lower overall loss for the location-based approach than for the address-based response. Still, loss rates of some 35% in a black hole case are not tolerable, and I will come back to how to improve this on a later slide. So I said we wanted to have two viewpoints on the problem. So the analytical model for mobile ad hoc networks is in fact a quite simple model that is easy to understand. And if you read a paper, you will say, okay, yeah, I agree to this. The model is based on probabilistic approaches combined with geometry. So for example, for the effects of the black hole attack, what we describe is the probability for the black hole being in a closer ring regarding the ADV ring search than the destination. This means that if a black hole is located in the same or closer ring than the destination, the route request will reach the black hole will be able to answer and will attract the traffic. The black hole is further away than the destination with respect to the ring search, then the route request will just not reach the black hole, and the black hole will have no chance to get active. So I don't want to go into the math here, but in fact, these few formulas are the core of the description of this black hole attack. There is not much more on this. So the effects of the location-based intrusion response we also describe by a probabilistic approach combined with geometry. So what we describe here is the quarantined areas and the effect that we have when the black hole moves. So the old quarantined area is still active. The black hole moves, will be active again, will get detected again, and will have a new area of influence where it can get active. And if we can describe this area and the number of nodes that will be located within this area, we can describe the loss that is caused by location-based intrusion response, and we can describe the loss that can be caused by black holes when they move for a certain distance. And still, the model is quite simple. So what you can see here is, in fact, the core of the model, not much more around it. What I want to show before I come to my last slide is the comparison of the model predictions with the simulation results. So what you can see here, the curves, in fact, are the predictions that were made by the model, and the confidence bars, so the intervals here, are taken from the simulation studies from the previous slides. And you can see that even if we have a quite simple model and we use heuristics to approximate side effects on the edges of the network area, we have quite good matches with our analytical model and the simulation studies. And this could be a hint that this is what we can observe in real-world scenarios. So, to come to the end, if you don't want me to continue, just to wrap this up, we've seen that address-based intrusion response in mainnet is not the way that should be done. Location-based intrusion response seems promising, yet we have to do some improvements. We have, because well-behaving nodes, bang nodes that could be used for to establish the network are excluded when they are in proximity to misbehaving nodes. The question is, how can we improve this location-based approach? And we studied two approaches. And one is harnessing the delay tolerance of applications. So if you consider something like short message services or email, then the transmission could just be delayed if you are in a quarantined area until you leave this area, and this should be then transparent to the user. So for the emergency response scenarios, it's just something like it's better to deliver an emergency call some 20 seconds later than never at all. What we found is that we can recover the functionality of the network subject to the loss caused by black holes nearly completely, so we can have some good put in the network of near 100% if we are able, or if we are willing to take transmission delays that, for the scenario that I just showed you, may reach up to several minutes. Second approach, if we have some more constrained communication regarding time, is to use an adaptive transmission power of the nodes, and this is just to minimize the size of the quarantined areas. This means that if I'm located closer to a well-behaving node than to a misbehaving node, I can try to adapt my transmission power such that I reach the well-behaving node but not the misbehaving node. And with this you can limit the size of the quarantined areas that are excluded from the network, and with this you can limit the number of affected nodes, of affected well-behaving nodes. So in fact, that's what I wanted to show you up to now. If you want me to, I can go into details of these delay-tolerant approaches and address-based and transmission power reduction. Otherwise, I would just end my talk here. Thank you for your attention and be open for questions.
Why don't we end here, and then any other further discussions you want to have, you'll have time here. But we can stop the recording. Okay?
Okay.